information in the memory of the quantum computer safely, robustly.
A quantum machine may have discovered a parallel universe shifter, according to a recent claim from quantum computing. This is a remarkable phenomenon. Prominent physicist Brian Cox has cautioned about the consequences of these experimental findings. If true, this discovery could shatter everything we thought we knew about reality. Could quantum computers be tapping into alternate dimensions to perform calculations? As scientists grapple with these mind-bending results, Brian Cox issues a stark warning. Are we on the brink of unlocking forces beyond our control? Overview of the claim. Recent advancements in quantum computing have produced outcomes that go against accepted notions of reality and computing. In a recent experiment, a quantum computer reportedly solved a computational problem in under 5 minutes, a task estimated to require a classical supercomputer an astronomical 10 septillion years. This outstanding performance has led some researchers to suggest that the machine may be processing information across multiple realities. Renowned physicist Brian Cox has publicly warned about the implications of these findings. He emphasized that the observed speed and efficiency may indicate that quantum processes are operating beyond standard physical laws. The claim comes from experiments conducted on advanced quantum systems that utilize qubits, which are capable of existing in superposition, meaning they can hold multiple states simultaneously. This unique property allows quantum computers to perform many calculations in parallel. In this particular experiment, the system's performance far exceeded the capabilities of classical computing technology. The experiment's data has generated a great deal of controversy among scientists. Some argue that the efficiency of the quantum computer suggests that it may be drawing computational power from parallel universes, a concept aligned with the many worlds interpretation of quantum mechanics. Brian Cox has advised the interpretation of these findings with caution. While the experimental outcome is undeniably impressive, Cox emphasizes that the evidence must be carefully examined before drawing any firm conclusions on the existence of parallel universes. He insists that additional testing and replication of the results are crucial. The core of the debate centers on whether the incredible computational speed is solely a product of improved quantum error correction and enhanced qubit coherence, or if it indeed points to a deeper phenomenon. Critics of the parallel universe's interpretation note that quantum mechanics, as it is currently formulated, does not require the existence of multiple universes to account for its predictions. Despite these differing views, the experiment has gone beyond what is considered possible in computation. Consequently, the claim represents both a significant technological breakthrough and a potential paradigm shift in our understanding of the universe. It pushes researchers to review fundamental theories and explore the possibility that our universe may be part of a larger multiverse. As further investigations are underway in multiple laboratories worldwide to replicate these results and rule out experimental errors, independent teams are analyzing the quantum data and verifying the computational benchmarks. This collaborative effort among scientists aims to establish whether these outcomes can be consistently reproduced, thereby strengthening the claim or suggesting alternative explanations. The pursuit of definitive evidence continues, driven by the promise of unlocking new realms in quantum physics and computational theory universally. But how exactly do quantum computers achieve these seemingly impossible feats? The answer lies in the very fabric of quantum mechanics, where reality itself behaves in ways that defy common sense. To truly understand why this experiment has sent shockwaves through the scientific community, we need to break down the fundamentals of quantum computing. Fundamentals of quantum computing. Quantum computing is a field that exploits the unique principles of quantum mechanics to perform calculations that are impossible for classical computers. Unlike classical bits, which exist as either 0 or 1, quantum bits or qubits can exist in a state of superposition, representing both 0 and 1 simultaneously. This ability to be in multiple states allows quantum computers to perform many computations at once, vastly increasing their potential processing power. Another key principle is entanglement, a phenomenon in which qubits become interconnected such that the state of one qubit directly influences the state of another, regardless of the distance between them. Entanglement creates a highly correlated system of qubits that work together to perform complex calculations. Furthermore, quantum interference, which arises from the wave-like nature of qubits, allows the constructive combination of correct solutions while cancelling out incorrect ones. The development of quantum computers involves overcoming significant technical challenges. Maintaining coherence, the property that allows qubits to stay in a superposition, requires extremely low temperatures and isolation from environmental disturbances. Error correction is another major problem, as qubits are susceptible to errors from even the slightest interference. Researchers have devised sophisticated quantum error correction methods, which involve encoding a single logical qubit into several physical qubits to preserve information. Recent advances have led to the construction of prototype quantum systems that demonstrate these principles in action. Experimental platforms, such as superconducting circuits and trapped ions, have shown promising results in achieving longer coherence times and more reliable qubit operations. These advancements are crucial for scaling up quantum systems to a level where they can solve practical problems that are intractable for classical machines. The theoretical framework of quantum computing is supported by well-established mathematics, including linear algebra and probability theory. Quantum algorithms, such as Shor's algorithm for factoring large numbers and Grover's algorithm for searching unsorted databases, illustrate how quantum computers can outperform their classical counterparts. These algorithms exploit quantum parallelism to achieve significant speed-ups in problem-solving. Understanding the fundamentals of quantum computing is essential to appreciate its potential and limitations. As research continues, further improvements in hardware and error correction techniques are expected to expand the computational capabilities of quantum systems. These advancements in quantum computing are theoretical milestones and also practical steps toward building machines that can tackle real-world problems. Quantum computing rests on core principles that differentiate it from classical methods. The phenomena of superposition, entanglement, and interference form a theoretical framework that has been demonstrated in controlled experiments. Researchers are now focused on optimizing qubit performance and reducing error rates to unlock the full potential of these theories. This foundational work is paving the way for the creation of powerful quantum algorithms with wide-ranging applications across science and industry. The experiment and its results. Recent experimental work in quantum computing has yielded unexpected results. In one notable experiment, a quantum system solved a complex computational problem in less than 5 minutes. According to estimates, performing the same calculation on a state-of-the-art classical supercomputer would require approximately 10 septillion years. This staggering performance discrepancy highlights quantum computation's immense potential and has led some researchers to explore alternative explanations for the observed efficiency. The experiment employed a quantum processor that utilizes superconducting qubits. These qubits were maintained at cryogenic temperatures to ensure minimal interference from external noise. The system was carefully engineered to maximize coherence time, allowing the qubits to maintain their quantum state for a sufficient duration. In addition, advanced error correction techniques were implemented to reduce the impact of operational errors, which are common in quantum devices. Data from the experiment indicates that the quantum processor achieved a significant speed-up by leveraging quantum parallelism. The technique of superposition allowed the system to evaluate numerous computational paths all at once. This parallel processing capability, inherent to quantum mechanics, is what enables the processor to solve problems that are practically unsolvable using classical methods. The results were measured using standard benchmarks, including random circuit sampling. This benchmark is designed to test the ability of a quantum computer to generate a specific probability distribution that is extremely difficult for classical systems to copy. The quantum processor's performance on this benchmark was outstanding, providing numerical outputs that were both quick and accurate. Despite the impressive performance, the interpretation of the experimental results remains a subject of debate. Some scientists propose that the observed speedup may be explained solely by technical improvements in quantum hardware. while others suggest that the system might be utilizing computational resources from parallel universes. The experimental team has documented their procedures and results in detail, and independent groups are now attempting to replicate the findings to ensure their validity. Thorough verification is a cornerstone of the scientific method, especially when the claims challenge established theories and push the limits of current technology. Further analysis of the experimental data is ongoing. Scientists are carefully benchmarking the experimental output against robust simulation models. Every procedural step, including qubit setup and real-time error mitigation, is well documented. This systematic examination seeks to identify underlying factors that contribute to the observed performance gain. Global collaborative efforts will ultimately establish whether these observations represent a revolutionary advance in quantum physics or just incremental technological progress. Robust validation is imperative to reach definitive conclusions. Ongoing collaborations and reproducibility studies are key to confirming these outcomes. Advanced statistical analyses are being applied to verify the reliability and reproducibility of the data. Only through comprehensive evaluation can the true implications of these results be determined. Future experiments are expected to differentiate among competing interpretations, while research teams deploy state-of-the-art techniques and high-precision instruments to monitor quantum phenomena at new scales. This means that ongoing innovation and careful investigation will shape the next era of quantum breakthroughs. Interpretation, parallel universes, and many worlds. One interpretation of the extraordinary performance observed in quantum computing experiments is based on the many worlds theory of quantum mechanics. According to this interpretation, every quantum event results in the branching of the universe into multiple, non-communicating realities. In this view, a quantum computer may be performing calculations across parallel universes at the same time, thereby achieving results that far exceed expectations. Supporters of this idea argue that the efficiency of quantum algorithms could be explained by the utilization of computational resources from these multiple worlds. Advocates of the many worlds interpretation point to the basic features of quantum mechanics, such as superposition and entanglement, as evidence that the universe does not collapse into a single outcome during measurement. Instead, all possible outcomes occur in separate branches. This perspective offers a radical explanation for the speed-up observed in quantum processes, suggesting that the system is effectively harnessing parallelism on a cosmic scale. The theory challenges standard ideas of reality and prompts a critical analysis of how computation is understood. Critics, however, caution that the many worlds explanation remains highly speculative. They emphasize that quantum mechanics, as it is currently formulated, does not require the existence of multiple universes to account for its predictions. Existing interpretations, such as the Copenhagen interpretation, provide an alternative framework where the act of measurement causes a collapse of the wave function into a single outcome. According to these critics, the exceptional performance of quantum computers can be attributed to advances in hardware and error correction without invoking parallel universes. Despite the controversy, researchers continue to explore whether the experimental results offer any direct evidence for the many worlds scenario, or if they can be fully explained by known quantum phenomena. The interpretation of these results carries profound implications for our understanding of both quantum computation and the nature of reality. In this context, the many worlds hypothesis remains one of several competing interpretations that continue to inspire more research and debate among scientists around the world. Further theoretical work is required to determine whether the many worlds framework provides the best explanation for quantum computational speedups. Researchers are investigating whether the unusual results could be a manifestation of quantum parallelism without necessitating the existence of multiple realities. In this pursuit, experimental data is compared against predictions from both the many worlds and conventional collapse interpretations. The outcome of these investigations will not only shed light on the nature of quantum computation, but may also influence our broader understanding of quantum theory. Researchers are currently updating existing theoretical models to include new findings, and they are developing new mathematical equations to understand the increased speed that has been observed. This progress in ideas is happening separately from improvement in experimental tools and is likely to lead to a better understanding of the basic principles that govern quantum behavior. Expert opinions and critical analysis. Expert opinions regarding the interpretation of recent quantum computing experiments vary widely. A variety of researchers, including theoretical physicists and computer scientists, have expressed feelings of both excitement and doubt about the possibility that quantum computers could be connecting with parallel universes. Some experts argue that the remarkable computational speed observed in these experiments can be fully explained by improvements in quantum hardware, such as enhanced coherence times and more effective error correction protocols. They maintain that conventional quantum mechanics, without invoking multiple realities, is sufficient to account for the results. Some well-known scientists have considered the possibility that the results of the experiment could reveal a more profound and unique phenomenon. Supporters of the many worlds interpretation suggest that the parallel nature of quantum processes serves as proof that the system might be drawing on computational resources from other realities. These specialists emphasize that the mathematical framework of quantum mechanics, especially regarding superposition and entanglement, naturally supports the idea of several outcomes existing at the same time. Critics of parallel universes warn against making quick judgments based on the findings of just a single experiment. They stress that it is crucial to have other studies confirm the results and to conduct thorough statistical checks to eliminate any chances of mistakes or misunderstandings. Some scientists have pointed out that even though experimental results are remarkable, similar claims in the past were often found to be due to advancements in technology instead of proving that a multiverse exists. Several academic papers and reviews have been published that debate the merits of these competing interpretations. The literature reflects a reasonable scientific discourse, with studies carefully examining both the technical aspects of quantum processes and the theoretical frameworks that underpin quantum mechanics. Many experts agree that further experiments, with improved control and measurement techniques, are necessary to resolve these issues definitively. In academic conferences and seminars, serious debates continue over the proper interpretation of the data. Some argue that the experimental results should prompt a re-evaluation of the foundational principles of quantum theory, while others call for a more cautious approach. The divergence in expert opinions shows the complexity of quantum mechanics and the challenges involved in interpreting experimental outcomes at the frontiers of technology. Overall, the critical analysis of the experimental findings illustrates the dynamic nature of scientific investigation. Researchers are working diligently to assess the validity of the many worlds explanation and to determine whether alternative, more conservative interpretations can account for the observed phenomena. Further experimental studies and cross-disciplinary research are being encouraged to address the uncertainties raised by these findings. Leading laboratories and research institutions are collaborating to replicate experiments, analyze results, and refine theoretical models. This collective effort is important for establishing a more comprehensive framework for understanding quantum phenomena. These critical analyses explain the necessity for ongoing, thorough scientific evaluation. Future experiments will clarify these issues. Brian Cox's warnings. Brian Cox has been a vocal commentator on the implications of recent quantum computing experiments.
So you basically calculate these little quantities, which are to do with something called the action, and you add them up.
In his statements, Cox has emphasized caution in interpreting the incredible computational results. He has repeatedly stated that while the performance of quantum processors is impressive, the data should not be quickly taken as conclusive evidence of parallel universes. According to Cox, the remarkable speed-up observed may be attributed to technical advancements in quantum hardware and error correction, rather than an indication of hidden multiversal processes. In his discussions, Brian has stressed the importance of careful experimental validation. He has pointed out that quantum mechanics remains a highly complex field, where theoretical models must be continually tested against empirical data. He argues that unique claims require unique evidence, and until further replication of the results is achieved, the hypothesis of parallel universes remains uncertain. His message is clear: focus on verified improvements in quantum technology rather than unproven theoretical interpretations. Brian Cox also stresses that public and media interpretations of these findings should be measured and based on solid research. He criticizes sensationalized claims that rush to conclusions about the existence of multiple realities without sufficient experimental backing. Instead, he advocates for a balanced view that recognizes both the technical achievements of modern quantum processors and the ongoing uncertainties in quantum theory. Brian Cox has always focused on making science easy to understand throughout his career. He points out that even though quantum computing is a big step forward, it is just one part of the bigger picture when it comes to understanding how the universe works. He reminds us that scientific advancements happen gradually, and we need to examine major discoveries closely before they change our basic ideas about physics. In recent interviews and public lectures, he has called on the scientific community to pursue further research and to remain open to all possible explanations. His words of wisdom encourage systematic approaches to resolving the debates that have arisen from these experiments without succumbing to sensationalism. His statements reflect his dedication to scientific accuracy and the careful examination of complex experimental data. His warnings reinforce the necessity for continued verification and thoughtful analysis before accepting conclusions that could fundamentally alter our understanding of reality. These measured warnings and precise observations form a cornerstone of Brian Cox's enduring commitment to advancing our understanding of quantum phenomena. He insists on empirical evidence always. Implications for quantum research and technology. The implications of the recent experimental findings extend far beyond the laboratory. These results represent a major advancement in the field of quantum computing, with potential applications that could revolutionize various industries. The dramatic speed-up achieved by quantum processors not only challenges classical computational limits, but also opens up new avenues for research in physics and computer science. The possibility that quantum computers may operate using resources from parallel universes, while controversial, has stimulated further theoretical and experimental investigations. From a technological perspective, the improvements in qubit coherence, error correction, and system stability demonstrated in these experiments are critical for scaling up quantum computers to practical levels. Such advancements could lead to breakthroughs in cryptography, optimization problems, drug discovery, and materials science. The ability to process complex data at very high speeds offers the potential to solve problems that are currently difficult for classical computers. Moreover, the experimental results have led to the critical examination of existing quantum theories. Researchers are now considering whether standard interpretations of quantum mechanics are sufficient to explain the observed phenomena, or if new theoretical models are required. This critical examination is driving progress in both experimental techniques and theoretical frameworks, potentially leading to a deeper understanding of the fundamental nature of reality. The impact on quantum research is also evident in the increased collaboration among international research teams. Laboratories worldwide are sharing data, methods, and insights to produce and extend these findings. This cooperative approach accelerates the pace of discovery and ensures that any new interpretations are subjected to rigorous scrutiny. Consequently, the experimental breakthroughs discussed here have far-reaching consequences for both the future of quantum research and technological innovation. These findings compel the science community to rethink long-standing assumptions about computational limits. The performance gap between quantum and classical computers, as demonstrated in the experiment, suggests that quantum systems can solve problems previously thought to be unsolvable. This realization is driving a lot of investment and research into quantum technologies. It also raises important questions about the scalability of current quantum architectures and the future design of quantum processors. As researchers continue to refine quantum hardware, they anticipate that these advancements will lead to practical applications that could revolutionize fields such as secure communication, optimization, and complex system simulation. The momentum behind quantum research is building rapidly, driven by both technological necessity and the need to find new fundamental principles. In short, the implications of these advancements are profound, promising not only to transform computational technology, but also to change our fundamental understanding of nature. These transformative insights are driving a new era of quantum research, where the convergence of theory and experiment will likely yield revolutionary applications that impact science, industry, and everyday life. As we look ahead, the next phase of quantum research promises breakthroughs that could take us beyond theoretical possibilities. But what will the future of quantum experiments really look like? Future directions in quantum experiments. The next generation of quantum experiments is set to open new frontiers in both technology and scientific understanding. Researchers are designing innovative experimental frameworks that overcome current limitations in stability and scalability. In these upcoming studies, the focus is on creating quantum systems that remain resilient under diverse conditions, ensuring that devices operate reliably beyond the controlled environment of the laboratory. Efforts are underway to increase the number of high-quality qubits and to extend coherence times, which are essential for transitioning quantum devices from experimental models to practical tools. A key area of development involves the creation of advanced error correction protocols. Present quantum systems suffer from disturbances that cause the loss of quantum information, so scientists are working on methods to protect qubit states better. New strategies combine hardware improvements with dynamic software controls that adjust operational parameters automatically. Early tests of these approaches have shown promising results, as experiments have achieved longer operational periods with significantly fewer errors. The ultimate goal is to design self-correcting systems capable of adapting to environmental fluctuations, thereby establishing a more stable quantum platform. Another promising direction is the integration of quantum components with regular computing elements to form hybrid architectures. In these systems, quantum processors perform specialized tasks that benefit from their inherent parallel processing capabilities.
How quantum computing can attain an advantage by performing computations in parallel worlds.
While classical computers manage routine calculations with high reliability, this symbiotic approach is expected to yield enhanced overall performance and enable the resolution of complex problems that neither system can solve independently. Future experiments will also target the validation of new theoretical models by exploring unexplored aspects of quantum behavior. Researchers plan to design experiments that detect subtle variations in particle interactions under controlled conditions. Such studies may reveal phenomena that challenge existing theories and prompt the development of new models. By pushing the limits of measurement accuracy, scientists hope to find effects that provide deeper insights into the fundamental laws governing quantum mechanics. International collaboration is a vital component of these efforts. Researchers from across the world are consolidating expertise, sharing resources, and exchanging data to build more advanced experimental setups. Joint projects and open research initiatives are accelerating progress and ensuring that findings are thoroughly verified. This collective effort is laying a strong foundation for the next era of quantum innovation. As experimental techniques continue to evolve and researchers refine their methods, the promise of quantum experiments to revolutionize technology becomes increasingly tangible. Overcoming challenges in system stability, error correction, and hybrid integration will not only advance quantum computing, but also broaden our overall understanding of nature. These sustained efforts mark a critical step toward unlocking the full potential of quantum technology and changing the future of science. This pursuit of improvement and collaborative research not only drives innovation in quantum experiments, but also opens a platform for transformative applications that will shape scientific progress and technological development in years to come. By improving methods and embracing global cooperation, researchers pave the way toward a future defined by revolutionary breakthroughs, quantum chip fabrication, and engineering innovations. The fabrication of quantum chips represents a fusion of advanced material science and precision engineering. Modern quantum processors rely on superconducting circuits created with ultra-clean deposition techniques. Specialized facilities use photolithography and electron beam lithography to pattern intricate circuit designs onto substrates such as silicon or sapphire. Materials like niobium and aluminum are chosen for their superconducting properties, which are essential for reducing electrical resistance and minimizing thermal noise. Engineers concentrate on achieving uniformity and minimizing defects at the nanometer scale, as even minor imperfections can disrupt qubit performance. To protect these delicate structures, quantum chips are integrated into dilution refrigerators that cool the devices to temperatures near absolute zero. This extreme cooling is vital for maintaining qubit coherence and ensuring stable operation during complex computations. Design innovations include optimized qubit connectivity and shielded circuit layouts to reduce interference from ambient radiation. Researchers employ advanced simulation tools to predict circuit behavior under varied conditions, enabling them to refine designs before fabrication. Additionally, improvements in on-chip error correction circuits are incorporated to detect and mitigate operational errors in real time. These engineering achievements are the result of close collaboration between academia and industry. By combining state-of-the-art fabrication methods with innovative circuit design, engineers are continually enhancing quantum chip performance and reliability. These breakthroughs are more than theory. They're shaping the future, but how soon will they impact our daily lives? Practical applications of quantum breakthroughs. Quantum research is about experiments and theory. It is also about turning scientific discoveries into practical tools.
Now, this is called the path integral formulation of quantum mechanics. That underlies everything else. You can get the rest from that.
Recent breakthroughs have shown promise for many applications that can change everyday life. In this chapter, we focus on how advances in quantum experiments are being used in fields such as computing, security, medicine, and energy, and how they may soon impact industries around the world. One major area is quantum computing for data processing. New quantum machines are designed to solve problems that are too hard for ordinary computers. These systems can perform many calculations at once, which helps in tasks like optimizing traffic flows and discovering new drugs. Companies are investing in these technologies, and small quantum devices are being tested to determine how they can speed up complex computations. Another important application is in cybersecurity. Quantum encryption methods promise to create secure communication channels that are nearly impossible to breach. With rising concerns about data theft and hacking, improved security is critical. By using quantum keys and encryption, sensitive information can be protected even against powerful adversaries. This technology may soon safeguard personal data, financial transactions, and government communications. Quantum technology is also making strides in medicine. Advanced quantum sensors are being developed to improve imaging techniques, enabling early detection of diseases. These sensors can measure tiny biological changes that standard devices miss. Early diagnosis leads to better treatment and improved outcomes for patients. Researchers are also using quantum simulations to study molecular interactions, which could speed up the process of discovering new medicines. In the energy field, quantum experiments are helping scientists design new materials that improve battery life and energy efficiency. By studying the quantum behavior of materials, engineers can develop more efficient solar cells and storage devices. This research may lead to cheaper, more sustainable energy solutions that benefit both consumers and the environment. Furthermore, practical quantum applications extend to finance and logistics. Quantum algorithms can solve optimization problems quickly, resulting in more efficient supply chains and better investment decisions. The ability to analyze large amounts of data using quantum methods gives businesses a competitive edge in the digital world. Global collaboration plays a vital role in these efforts. Research groups from many countries share their findings and work together to test new ideas. This international teamwork helps verify breakthroughs and speeds up the development of practical quantum technologies. practical applications of quantum breakthroughs are advancing rapidly. As research and engineering improve, these technologies will start making a real difference in many industries. The move from laboratory research to practical use is already underway, promising to change computing, security, healthcare, and energy in the coming years. These ongoing advancements mark a turning point for quantum technology, setting the stage for innovations that will benefit society and the economy. By bridging the gap between laboratory research and practical implementation, quantum breakthroughs promise a future where science and technology work together to solve the challenging problems of our time. Thank you for watching our exploration of quantum breakthroughs. Stay tuned as we will be dropping more exciting videos.